Did you know that the basis of a power electronic design is the interaction of power losses of an IGBT discrete or module with the thermal impedance of the power electronic system? By using a precise model, the system can be designed for high output current without exceeding the maximum junction temperature limit while remaining reliable in terms of power cycling. Stay tuned if you want to learn how to characterize the thermal properties of a power electronic system and how to model it for application-oriented investigations. We will start with an overview of some relevant concepts. The first one is ZTH. The thermal impedance that is relevant for the module and the discretes datasheet is divided according to the type of module package and heat transferring agent into inner impedance and outer impedance. However, it can also be designed as total impedance. In this case, J stands for junction, C for case, and H for heatsink. ZTH x to y is defined as the quotient of the difference between the temperature that applies to the positions x and y and the heat flow of the power flowing through those sections. The value of P is calculated from the losses in the semiconductor. But what's the difference between the transient thermal resistance and thermal resistance? Well, thermal resistance corresponds to the ZTH that sets after an infinitely long time in which the thermal system is stationary. Also, the junction temperature determined in this way is an average value, which is why we speak here of a virtual junction temperature. In switching mode, the temperature in a chip is not homogeneously distributed, but a temperature field is formed over surface and volume. Finally, the heatsink temperature is to be determined by a sensor. For this purpose, a hole must be drilled in the cooling unit under the heatsink surface perpendicular to the chip plane, so that the sensor located in this hole is below the center of the chip. The sensor must record the temperature. The basic principle of measurement is described in the standard IEC 607479. To determine the thermal impedance, a constant power is fed into the IGBT by a current flow, so that a stationary junction temperature is reached after a transient period. After turning off the power, the cooling down of the device is recorded. On the other hand, thermal resistance is the difference between two temperatures, Tx0 and Ty0, at T equals 0 divided by the power. To calculate the time-dependent thermal impedance, the recorded temperature curves need to be vertically mirrored and shifted to the origin of the coordinate system. Then, ZTH is calculated by the temperature difference divided by the power. For determining the junction temperature in the cooling phase, a defined measurement current is fed into the device, and the resulting saturation or forward voltage is recorded. To define a very small current, it is possible that Iref reaches values up to 1000 I-nom. The junction temperature can be determined from the measured forward voltage with the aid of a calibration curve, in which the junction temperature is a function of the voltage drop of the IGBT or diode at the reference current. Its reversed curve is recorded earlier by means of external homogeneous heating of the tested module. The case temperatures and the heatsink temperatures are determined by means of thermocouples. These thermocouples are thermally isolated except at the top. This is where they come into contact with the base plate of the module and the heatsink respectively. In both cases, the projected thermocouple axis is located in the center of each chip. Precise measurements are required for determining junction temperature and case temperature at the exact time the cooling phase begins. It should be pointed out that, directly after turn-off, the smallest thermal time constants lead to big changes in the virtual junction temperature, so this is a very important time period to measure. On the other hand, oscillations also occur at this time. These make the measurement very difficult. The parasitic effects lead to transient disturbances in the measured signals. In order to overcome the huddles mentioned above, a modified measurement system is being used. The measurement results are evaluated in part automatically by the measuring station software and are to be checked and completed by the orderer. The respective thermal resistances, RTH values, are calculated as follows. Moreover, the following applies analogously to the calculation of thermal impedance. Hopefully this video was interesting and provided you some hints on thermal resistance and measurement principles for discretes and modules. If you need additional information, just have a look at our website at Infineon.com. And don't forget to subscribe to Infineon's newsletter for engineers.